I do archery. I've got a small range set up in my closet at home. I can practice. That's nice. All right. Oh, and Mariah has made it. Excellent. Everybody's here. Good, good, good. Then we should officially begin. Good afternoon, everybody. Once again, my extra screen is not cooperating, so if you want the visual aid, you will need to join the Zoom call so you can actually see it. It feels so weird because you're all here. I'll figure this out. Staying late today, I'll figure this out. That or throw this darn machine away and get a new one. I don't know. Anyways, today we are rushing through our review of the geometry basics. We're going to hit on quadrilaterals and circles today. But before doing that, let's review our stuff from yesterday. Here are answers for the polynomial and triangles section. I believe we last left off with the diagonals for the dodecagon unfilled in, so that's 54. Dodecagon. Yes. And so if you went the extra mile to find the formula for number of diagonals in any polygon, that would be this guy up here in the corner, n times n minus 3 all over 2. It's handy. It's a nice convenient shortcut, not needed. There might be occasion on the SAT where it'll save you a lot of time if you know this formula, but it is not required for any of my tests this year. And moving right along, here is my completed concave pentagon. Notice because they tell you the diagonal, external diagonal is supposed to be ET, and the letters always go in order around the shape, usually clockwise. N, because it's in between the E and the T as they give it, should be the point between E and T on the shape. That should all be logically consistent there. And then the equilateral triangle, sorry, I'm so used to triangle. Equilateral quadrilateral, that's a lot of laterals. As we will find out today, is called a rhombus. And looks something like this. Please do mark angles Q and U with a different number of tick marks so that you are sure they are definitely not congruent. Indicate as such. Although it's pretty obvious to tell, like one's acute, one's obtuse, let's be extra sure and mark it up. All right, and then 15 through 18. Notice the letters are in a given order for a reason. These shapes correspond in the same order. So MNOPQ corresponds to RSTUV. N is the second letter, S is the second letter. So N corresponds with S. This angle corresponds with that angle. This one will be 82 degrees, same as that one. And upon thinking about this a little further, the way to make that happen, if you wanted to put one shape on top of the other shape and make it all line up, you'd actually have to flip it over. And that is perfectly allowed. Instead of, I just showed it rotating before, you actually need to flip it. It's like a pancake, okay? Totally doable. We didn't actually change the shape at all. And then finally, a regular pentagon. Regular means all sides are the same length. So we can take 31 and divide it by 5 to get the length of each side. Any questions on that page? Excellent. Next page. Here are some possible answers to the finding pairs of things. But again, there's multiple answers for this. I'll talk a little bit about each one. The parallel lines are only these two lines on the top and the bottom. We're not sure that the middle one is perfectly parallel. Could be just slightly crooked. So the way to name the top line has to use letters A and B in whichever order you like. The bottom line, you could use any two letters. You could use GH, you could use HI, IG, whichever ones you like. The perpendicular segments. There is only one angle indicated as a right angle, which means only this segment and this line we know to be perpendicular. So your answer must come from those. You can use any two letters you like from here, and you can use any two letters you like from here. You could say that CD is congruent to BF. Even though they don't actually intersect, they would still be perpendicular. Yes? Yes, so you can swap the order of the segments. That doesn't change parallel. Right? And you can swap the order of the individual letters. You can say IG is parallel to segment BA. Right? As long as you don't have a direction on there, the order does not matter. Right? A ray has a direction to it. It's got, only one end has the arrow, so which order you put it in can make a difference. Similarly, angles. One of those letters is in the middle, so that one better be in the middle. Otherwise, it usually doesn't matter which way you write it. Angle BAD could be DAB. Right? That works too. I'll get to that one. Congruent segments. There is only one pair of congruent segments as marked. It has to be this segment. It has to be this segment. Again, you can swap the order of the listing, you can swap the order of the letters inside, but it must be that combination. And I'm going to skip 4 and come back to it. 5 is a little simpler. A linear pair, or actually a linear set, would be angles that form a line. Right? So look here at DEG and GEF. They combine and they form this straight line right there. That's what makes the angles linear. So that's one example. There's a lot of them on this page, right? ADC, ADE. They're all going to share that vertex in the center. There's lots of combinations there. Interestingly, every linear pair of angles will also be supplementary. So any answer you have for 5 could also be your answer for 4. Anything that meets this will also meet that. But there's some additional types of pairings here that would be supplementary, and that's an example I gave here. I used BAD and DGH. So those two angles are actually supplementary because of the parallel lines. We'll talk more about that in a couple of weeks, or maybe next week, about the properties of parallel lines, and it will create a set of supplementary angles there. But that is one of them. There are some more possibilities, and I wanted to highlight that. You could go the other side, right? These two would be supplementary. All right, moving on. The triangle drawings. Here is the rest of triangle tri. You could swap the R and the I, but T, remember, had to be between the two congruent sides. Here is one arrangement of my scalene right triangle. You could have used any of these 3 letters to be the right angle, S, C, or A. It didn't specify. But all of the midpoints are specified on which segment they go on. When it says respectively, that means, the order matters here. The first goes with the first, the second with the second, and so on. So make sure your L is between S and C. And make sure you have marked your segments. The only way to know L is a midpoint is because you've told me it's in the exact middle. Both halves are equal. You have to mark both sides of your midpoint as congruent to each other, but not congruent to any other segment on the triangle. it is supposed to be scalene. So all three sides need different numbers of marks. It didn't matter which mark you put where, so long as these two match, these two match, these two match, and nothing else. Okay? And then finally, on the coordinate plane triangles, here is one possible answer for each one. I'll talk about all of the possibilities here. It's relatively simple to generalize. Your point F can be anywhere along this vertical line, and it will still make a right angle here at B and be a right triangle. So if you have an 8 for your x value on F, it is correct. Similarly, you could also have put it here and put the right angle on this side. So if anywhere on the y-axis, if your x value is a 0 for F, it is correct. Either of those options will do. To make an isosceles triangle, since we have to include AB already, there's no way we're going to match that segment with some funky diagonal here. So the only way to do it is to put it in the middle and make these two congruent. So your D has to be between A and B perfectly evenly. It must have an x value of 4. It can be anywhere up or down on this vertical line. So long as your x value is 4 for D, it is correct. And then finally, G wanted to be a scalene triangle that is not right, which means pretty much it just can't be any of the above. So as long as your G has an x value that is not 0 or 4 or 8, it can be anywhere else, it'll probably be correct. If you go into fractions, it's possible to find some point where AB is congruent to GB. But if you're sticking on the integer grids there, I don't think we're going to make that happen. All right, any questions on that page? All right, let's move on to today's topic. I need copy number 2. Quadrilaterals. So we're going to run through the basic properties that define the quadrilateral. There are additional properties. Each one has, as a consequence of its setup, additional interesting features that we could look at and compare. We'll get to when we get to the week of quadrilaterals. But for right now, I'm just not, what is the basic definition required to be this particular shape? And we start with the parallelogram. In order to construct your quadrilateral into a parallelogram, you need 2 pairs of parallel sides. So usually we draw them at a slant like this because it's not a rectangle necessarily. All we know is that this side is parallel to that side, and the left is parallel to the right. Obviously, the top is not parallel to the left, so use 2 different sets of marks there. Opposite sides are parallel. If both sets of opposite sides are parallel, you are automatically a parallelogram. Many other features follow, but that's the minimum requirement. Then, you could get more specific with your parallelogram. If you also force all 4 sides to be the same length, then you will have a rhombus. So a rhombus is a more specific type of parallelogram, so it needs all the same features drawn in, 2 pairs of parallel sides, and an extra tick to tell me all 4 sides are congruent. You could put 2 ticks on each one if you want, so long as each side has the same number of straight tick marks to show all 4 sides are congruent. That makes it a rhombus. And then we can go even more specific. If you take a rhombus and force all 4 angles to be congruent, they will, by definition, have to then be right angles, because 360 divided by 4 is 90. So we are still a parallelogram. We still have two pairs of parallel sides. We still have all four sides are congruent, and we have right angles in all four corners. That makes it a square, the most specific of shapes, or at least of quadrilaterals. And then to complete the family tree here, let's go back a couple steps. Take your parallelogram and straighten him out a bit. So you still have two pairs of parallel sides, but now we force all four angles to be congruent. Without worrying about the sides yet, we end up with the rectangle. Opposite sides are parallel, and all four corners are right angles. Right. All four of these are parallelograms. These three are just more specific types of parallelograms, depending on what you force to be congruent. Make the sides congruent, you get a rhombus. Make the corners, the angles congruent, you get a rectangle. And if you do both, you get a square. So a square could be described as a rectangular rhombus or a rhombic rectangle. It's both. All right, that's those guys. I will leave filling in the specific letters up to you. As well as number 6, they want you to list some lengths for the sides that has such a perimeter. Now, the other two shapes are the like lost cousins of the family. All right, they're related, but not as intimately. A trapezoid is defined as a quadrilateral with exactly one set of parallel sides. Okay, not two pairs. So only two of the sides are parallel. You could draw a trapezoid like this. In fact, people often do. However, the one they want you to draw here, notice there's the perpendicular sign. We've got to make a right angle somewhere. So I'm actually going to tweak this a little bit and make this guy a right trapezoid by making one of these a right angle. And these are my parallel sides. Oh, that top one looks awful. There we go. And at least one right angle. That makes a trapezoid. It has exactly one pair of parallel sides. A parallelogram is not a more specific trapezoid. Now, I wasn't going to talk about consequential properties, but I will mention one. It turns out, in a parallelogram, if you force opposite sides to be parallel, it also automatically gives you opposite sides congruent to each other. It will have that. That's not the definitional property to make it a parallelogram. It's an immediate consequence thereof. And we could spend a whole day exploring like how to prove that. It's kind of interesting. But keep that in mind. A parallelogram has opposite sides that are congruent. It has still two pairs of congruent sides. And this is what differentiates it from our final shape, the kite. A kite also has two pairs of congruent sides, but they're not opposite, they are adjacent. So I'm going to put the two short sides right next to each other and the two long sides next to each other. Pretend that's actually a straight line. So two pairs of adjacent congruent sides, saying nothing about the angles or parallelness, just has to do with the length. That's what gives us a kite. And it looks exactly like the thing you would expect to go fly on a windy day. Okay? Questions about special quadrilaterals? All right. The last couple of questions on that page have you name the quadrilaterals from this grid of figures. All right, we're going to assume the grids are like perfectly square and even, so this is a length of 1, that's got a side length of 2. All right, so you've got to figure out which combination, okay, that's congruent to that piece, that makes it this one's the what? All right, and then name them properly. Fairly straightforward. Do notice, I highlighted here 4, it's named trap, which means the 4 corners need to be called T, R, A, and P in that order. You can start anywhere you like, working your way around. But this refers to RE is perpendicular. Oh, where's E? E is not in the name. So there's an additional point that is not one of the vertices that you must add a point E on top of your trapezoid to make it meet this criteria. Keep that in mind. It could be a midpoint. That is not specified. Right? There's nothing in here about lengths of sides needing to be congruent there. So it could be 1/3 of the way up a side. That'll be up to you to determine. All right. Now for circles. So circles, there's a few things you probably already know, and we've got a few things that are probably new. So let's just cover all the basics here. This is our circle. The outside ring of points is the circle itself. It's not a solid disk, just the points around the outside. And we would call that guy by its center point. So this is circle O, because the center point is labeled O. Our shortcut symbol for circle is a circle with a little dot in the middle. So that is also circle O. Right, just like how we have a triangle, A, B, C. Right, we've got a little symbolic form for shortcut, because mathematicians are lazy, and I try to avoid writing as much as possible. All right, the 2 great big features everybody knows about circles is the segment all the way across the circle is called the diameter. So here we have diameter segment QP. And then half of the diameter you get radius, in this case OP. The radius always goes from the center of the circle to the outside of the circle, and anywhere on the circle the radius is the same length. All of these possible positions for a radius are the same size. That is, in fact, what defines a circle. The circle is literally all of the points that are a given distance from the center. Everything that is 2 inches away from this spot right here, that's the circle. Okay? And people often forget that. You'll be in the middle of some geometry problem, puzzle-looking thing, and the solution comes from the fact that, oh, these are in the same circle. They're actually, those are the same distances, because those are both radii of a circle, right? So it's a very handy feature to have. That's the old stuff, though, right? You probably heard those terms in 3rd grade. Here's the new bit. Down here, you see that 48 degrees. That guy is called a central angle. Okay? And it's called a central angle because it's an angle that goes to the center of the circle. So we're going to call it an angle QOR. Right? A central angle has its vertex on the center of the circle. If this middle letter is not the center of your circle, you ain't a central angle. For example, if I drew a segment like that, that's not a central angle. That pink thing is just some random angle randomly hanging out in my circle. It's not central. However, we do have another specific type of angle we could draw in here. They haven't used this one yet, but we'll get to it soon enough. And that would be this kind of angle. If your vertex is on the edge of the circle, then you are an inscribed angle. The inscribed angle and central angle are two main types of angles we will have in a circle. We'll talk more about what inscribed really means on question 5. But here's an example of an inscribed angle. Now, inscribed angles have their own unique set of features. The central angles, though, are super important because the central angle also defines an arc, right? So if the central angle looks like your slice of pizza, the arc is the crust. And so we can talk about an arc from Q to R. And we're going to draw an actual curved piece above the letters. Okay? This is not a segment. This is an arc. It is part of the circle. It's not the whole circle. It's a piece of it. And so it has some curvature to it. But again, it is not the same as if I were to connect those with a straight segment. Right? This is not congruent to segment QR. Not the same thing. Arc is different. It also connects those 2 points, but it actually goes around the circle, not straight across. Okay? But then the key piece of this, the part that connects it to that central angle, comes from the measurement. And the measure of an arc will be equal to the measure of the central angle. That's what makes central angles so special, is they define the measurement of the arc. So in this case, arc QR would also be called 48 degrees. And it is the measure of arcs that all of the questions over here are asking about. All right? So we have one of them. We know QR is going to be 48 degrees. How do I find out the rest of them? Well, I need to know how many degrees it is all the way around the circle. What is the measure of a full circle? Does anyone know? What was that? 360, yes. Right? Skateboarders would know this, right? You do a flip and spin all the way around, you do a 360. Okay? 360 degrees all the way around the circle. And then let's have, I want to see it typed in Zoom. Tell me then how much is this much? What would that central angle be? The one here in brown. All right, Jenny's got it. This is half of the circle. A semicircle would be how many degrees? Type it, type it. If you're in the Zoom call, just type it in the chat there. Yep. There's 4. Very good. Yes, that's 180 degrees. Now 180. So if someone said one thing yesterday, and then today they're saying the complete opposite, say, hey, you've done a complete 180. They've spun around backwards. Do not say they've changed their mind and done a complete 360, because that's all the way around. They're turned and now they're facing the same way. Okay, doing a full 360 changes nothing. All right? Doing a 180, now you're the opposite. Right? Half a circle versus the full circle. So with those two measurements in mind, you should be able to add and subtract and figure out the measurements of the rest of the arcs there. All right. 3 more things to cover. We've got these 2 vocabulary terms, inscribed and circumscribed. So just like this angle here was an inscribed angle, we can also inscribe a whole shape. Scribe means to write. So inscribed means we're going to write inside. So inside of this circle, we are going to draw a pentagon, which got moved around somehow. It doesn't have to be a perfect pentagon, but in order to be inscribed, it does have to be not just inside the circle anywhere. Every vertex needs to be on the circle. So when you see inscribed, remember, it is inside the circle with the vertices on the circle. Not just, hang on, let me hold it so it snaps, right? Not just any pentagon inside the circle, all right? That guy is not inscribed. This one is. And then I bet you could guess it, but a circumscribed quadrilateral, just like circumnavigate means to go all the way around the globe. If you circumnavigate the globe, you've traveled around it. Circumscribed means to be written around. So we still have, relative to our circle, except now we have a quadrilateral on the outside of our circle. And not just anywhere on the outside. It needs to still touch the circle, just like our inscribed pentagon did. Except we can't get the vertices to touch the circle. This time, the sides are going to touch the circle. So a circumscribed quadrilateral will be outside with the sides touching the circle. Right? And that point right there, where it touches just that one single exact spot, we would call that a point of tangency, or a tangent point, a tangent line. That's where the term tangent means to touch. And it just goes boop at that one spot. Be careful, like if I really zoom in here, you can probably see, this isn't quite perfect. My circle, there's a little bit of a lump on the outside of my line. If I was to zoom in, it would look more like this, right? So my line actually goes through 2 different points. That's not good. That's not a tangent, all right? So try as best you can. Obviously, you're doing it by hand. It's not going to be perfect. That's okay. But, from whole page level, it should look good. Right? Looks like it only touches at the one spot. Don't run through the circle. All right, that's circumscribed and inscribed. And then we got one final thing, the very last bit, and that is a circle on the coordinate plane. This one can be a little tricky for you, right? SAT loves to mess up geometry by throwing a bunch of extra algebra on top of it. You're diluting my pure, perfect mathematics here. That's okay. I'm actually going to start with a different circle. Let's think of, zoom in here a little bit. Let's think of the unit circle. The very basic guy, centered on the origin, which didn't do a very good job there. That's better. So his center is right there at 0, 0, and it has a radius of 1. If that's a distance of 1, then I have these 4 points on each stem of the axes is 1 away in a different direction. So this is 1 in the positive x direction, 1, 0. This is up here is 1 away in the y direction, 0, 1. And we have the negative x direction and the negative y direction. That's our unit circle. That's the standard. Every circle is some transformation of that. It's either bigger or smaller and shifted around. Which means we will always have those 4 points in the 4 cardinal directions. Think of this as a compass rose, will be the 4 easy points to find on the circle. Okay? No matter how big or small it ends up being. So apply that to this guy over here. We know the center is right there. We have 1 point that is this far away. Use that to determine what its radius will be. And then we know the circle should end up looking something like that. However far away this one is, there'll be 1 straight down, 1 straight up, and 1 straight to the right. That same distance in all 4 directions away from the center. Okay? So you need to find that distance between those points and then add and subtract it to the appropriate x or y coordinate to get your coordinates for the other 3 points. That's circles on the coordinate plane. Not actually that involved, but it does require you to think a little bit differently. Okay. Any remaining questions on circles? No? All right, then you have, what do we got, like 7 minutes left to finish up the rest of these questions? Turn it in by the end of the day, and we'll wrap it there.